Welcome back to the lecture series on the engineering chemistry. This is a series of lectures given on basic chemistry under the auspices of the National Program on Technology Enhanced Learning funded by the Ministry of Human Resource Development. Today we will continue with the lecture on harmonic oscillator. This is the fifth lecture. In the last lecture we talked about how to solve or how to study the solutions of harmonic oscillator from the point of view of quantum mechanics. We will continue with the harmonic oscillator. We will look at the solutions and graphically we shall represent the functions that were written down in the last lecture. You might recall that these were written as Hermite polynomials multiplied by a Gaussian function, that is an exponential of minus x square type functions. So graphically we will see today how these functions are represented and what do they, the squares of these functions also we will see, which represent probability densities. The summary of today's lecture as organized for the rest of the lecture is like this. We shall discuss pictorial representations of the harmonic oscillator solutions, and then we shall introduce the Schrodinger equation for the electron in the hydrogen atom. This is of fundamental interest to chemists. Depending on the time, we will try and see if we can proceed towards the separation of the wave equation in spherical polar coordinates, and the solutions of course will not be done today but will be part of a series of lectures on the hydrogen atom. Okay. Let me continue with the harmonic oscillator. Recollect from the last lecture that we wrote the harmonic oscillator solutions psi n of x as a normalization constant and the Hermite polynomial root alpha x, where alpha was defined in terms of the constants which appear in the Hamiltonian Km by h bar square. K is the force constant, m is the mass of the oscillator, h bar is the Planck's constant divided by 2 pi, an exponential minus alpha x square by 2 here. And you remember the solutions for this problem, the quantized solutions or the energy levels quantized are given by the formula h nu into n plus a half, and nu was given as 1 by 2 pi square root of k by m. The quantum numbers n were given from the solutions as having the possible values of 0, 1, 2, 3, etc., including the value 0. Okay. The simplest of these solutions, when we did psi 0 of x, excluding the normalization constant right now, the Hermite polynomial and the exponential of minus alpha x square, including the Hermite polynomial for 0th order, which is a constant. You recall the ground state harmonic oscillator solution was e to the minus alpha x square by 2. Okay. Ground state referring to the fact that the quantum number is the lowest, and this is the least possible energy that can be associated with the harmonic oscillator if we accept that the harmonic oscillator is quantum mechanical, if we accept that the Schrodinger equation governs the motion of the harmonic oscillator both in space and in time. We are only looking at the spatial solutions. If we accept that, we come up with the requirement that the energies for the harmonic oscillator are non-zero even when the quantum number is 0. A solution e to the minus alpha x square by 2 you remember that the limits of x were from minus infinity to plus infinity, and therefore a plot of this function, if we plot symmetrically on both sides, let us say x is equal to 0. Let me remove this line. If we plot this, e to the minus alpha x square by 2 is an even function, meaning psi naught of x is equal to psi naught of minus x. Okay. It's an even function, and this value, the maximum value, is of course the constant that is associated with the ground state wave function, the normalization constant, and the value of this function at x is equal to 0 is 1, therefore that is this. And the function per se does not have any zeros anywhere, it does not go to 0 anywhere except at both the extremes, namely x is equal to plus infinity and minus infinity. Okay. This is a very well known function in mathematics and physics, in distributions, in the theory of distributions. It is known as the Gaussian function or bell shaped. In colloquial language, it is a bell shaped function. The Gaussian function can be normalized. When you talk about normalization, what you mean is this square psi naught x. Since these functions are all real, we do not need to worry about the complex conjugation. The domain of the harmonic oscillator is minus infinity to plus infinity. This is the normalization integral for the harmonic oscillator, and this should be set to 1. The Gaussian function can be integrated quite easily. There are standard formulas available for this. E to the minus alpha x square dx. When you take the square of psi naught x, this should be set to 1. Therefore, the value that you get out for this integral, which is root pi by a, root pi by alpha, okay. This has to be taken into account in the definition of the psi naught, so that this integral is equal to 1. If we multiply, then psi naught by, instead of the constant, if we multiply this function by alpha by pi to 1 by 4, then the integral of psi naught x dx between minus infinity to plus infinity will be 1, and therefore this is the normalization constant for this problem, okay, for this particular wave function. Likewise, you have to obtain the normalization constants for each one of these harmonic oscillator eigenfunctions. Okay. The summary of the harmonic oscillator wave functions are given here for you to refresh. The wave function is the normalization constant, Hermite polynomial exponential, and the energy is as what I have written. Okay. The one other thing that was emphasized in the last lecture was that the harmonic oscillator energies, as n increases from 0, 1, 2, 3, 4, etc., are equally spaced. For n equal to 0, it is half h nu. For n equal to 1, it is 3 halves h nu. For n equal to 2, it is 5 halves h nu, and so on. So if you look at this particular picture, the harmonic oscillator energies are plotted here, and this is the classical potential energy curve. In this picture, it does not have any role. This is the energy axis, and this is only to mark the classical spread of the potential energy, the x value, and you see the lines here representing the harmonic oscillator energies: half h nu, 3 halves h nu, 5 halves h nu, 7 halves h nu, and so on. So the distance between any pair of nearby energy levels is the same, and that is equal to h nu. That is En minus En minus 1 is h nu for all n. N minus 1 should be 0, so the lowest level is E0. If you go in E0, E1, E1, E2, all of them, it is equidistant. Okay. Now let us see the graph. Let us give the graphical representation for these functions for higher, that is the wave functions for n 1, 2, 3, etc., or what you call as the excited states of the harmonic oscillator. Okay. Let us look at the solution for H1. H1 of x root alpha x is 2 root alpha x. Therefore, the wave function psi 1 of x is without the normalization constant. We can always include that later. It is 2 x e to the minus alpha x square by 2. This is the first excited state wave function. We call it excited state when the quantum number is not the lowest, is not the least value. When the quantum number is 1 or 2, they are called the first excited, second excited, third excited state, and so on for the harmonic oscillator. The first state, the wave function is given by this. If you were to plot this, you see that psi 1 of x and psi 1 of minus x are related to each other, not by this one. This is the same because it is x squared, but there is x, so that the relation is minus. This is odd function. Therefore, with respect to x is equal to 0, whatever is the way the graph is on the positive x, it will be the exact negative of that in the x is equal to less than 0 domain. So if you plot this, again with x 0, if you plot this function, because it is x multiplied by x, at x is equal to 0, the function is 0. Okay. And the function is negative, therefore it goes to it goes to 0 as x goes towards minus infinity from the negative side, and it goes to 0 on the positive side from positive values. Okay. If you draw this carefully, there is no inflection here. Okay. So this is a continuous function x psi 1 of x, x e to the minus alpha x square appears like this. Okay. So let's see this particular graph where these functions are plotted. Okay. There is a node. This value, this point is called the node because this is where the function goes to 0, and that happens at x is equal to 0. The next function is the harmonic oscillator wave function psi 2 of x is not 2x but rather 4x square minus 2 multiplied by e to the minus alpha x square, and this is by analogy with the previous wave functions, this is the same whether x is plus or minus. So this is an even function. Therefore, it looks to be the same both ways, whether x is less than 0 or x is greater than 0. If you call this the psi x axis, 4x square minus 2. Therefore, at x is equal to 0, the function is a negative function, negative value. This is 1, and it is symmetrical. So the value of the function is normalization constant multiplied by minus 2. It starts somewhere there. And then the function goes through a maximum before it goes to 0. Okay. Goes to 0 on either side, and these two peaks are the same, maxima are the same. Okay. So you can continue to plot these wave functions, and that's what you see here: n equal to 0, n equal to 1, n equal to 2, n equal to 3, 4, and so on, and these functions alternate between odd and even characters. N equal to 0 is the even function, n equal to 1 is the odd, and then even and odd, and so on. If, I mean, much as we plot the eigenfunctions, even more interesting is not the function themselves but the square of the functions, because the square of the functions calculated in a small region multiplied by a small region give you the probability that the oscillator will be in that region. So if you look at the square of the functions, then that's given in this side. These are all the various quantum numbers: n equal to 0, n equal to 1, 2, 3, etc. And what you have is the psi naught square, psi 1 squared, psi 2 squared, and so on, and the number of nodes, that is the number of places where the function goes to 0, is the n value. If n is 1, there is 1 node; if n is 2, there are 2 nodes; n is 3, there are 3 nodes, and so on. Now this is a picture that we have to see a little bit more carefully with respect to what we understand as harmonic oscillator in the classical sense. If you let me just draw the psi naught square plot. At x is equal to 0, and this is the minus infinity limit, this is the plus infinity limit, and this is the psi of x. What you see here is that the probability of locating the harmonic oscillator in the region close to x is equal to 0 is quite high compared to the probability of locating the harmonic oscillator in either of these regions. The graph is symmetric, so it does not matter which x you have, plus or minus. The probability decreases, the square of the function decreases. So if you say psi naught square of x dx, if you calculate that for a small range dx centered at about the value x, you see that it is maximum at the center and it uniformly gets reduced as you go farther and farther away. What it means is that the likelihood of finding the harmonic oscillator in the region centered at the equilibrium position is the maximum. Okay. Classically, if you recall, as the harmonic oscillator vibrates, oscillates between both extremes, classically you know that the velocity of the oscillator is 0 here, and therefore this is the point where the oscillator seems to spend the maximum amount of time. The probability of locating the oscillator on either extremes is higher than the probability of locating the oscillator right in the middle. It really runs fast right in the middle, and at the extremes you see that it's possible that it spends more time, or the likelihood of locating the oscillators at either extremes of the classical domain is not what you see in quantum mechanics. You see the contradiction right away. The probability of finding the oscillator right in the middle region is high. If this is controversial, the next state of the harmonic oscillator is even worse, because the next state, when you plot the probabilities, the squares, this is not the graph you get. The graph that you get for the psi 1 square is, you see, the probability is practically 0. I mean, the function goes to 0 anyway. I should be careful in saying the probability is not 0, but it's very small. Okay. psi 1 x squared, and this is positive x and this is the negative x. Okay. If the oscillator energy is slightly higher and it is in the first excited state, the probability of locating the oscillator in this region is much smaller than the probability of locating the oscillator in this region or further down. What is important in all of this is that association of the classical ideas with quantum mechanical ideas can get you into trouble very, very quickly. Okay. If we do not understand the solutions as they are, but rather try to associate what the solutions mean and what classical results mean, you will see that classical results and the quantum results are at their most variance when the energy of the system is low and when the particle mass is very low. That is, when the quantum effects are really important, you see you can't draw the same conclusions or you can't draw analogies from classical results. These are all important with respect to molecular vibrations, because when you talk about molecular vibrations, it is we do see what is the region of high probability or low probability, etc., and this is particularly useful when one studies electronic spectroscopy later on. Okay. So please remember that from the squares of the wave functions and from the plot of the squares of the wave functions and the analogy for the probabilities, that we have some interesting conclusions that need to be kept in mind. Okay. Okay. Let me summarize the solution today and then we will move on to the hydrogen atom. Okay. So first one that comes as a surprise is that the energy is not 0 even when the quantum number is 0. The oscillator is never at rest. This was explained in the last lecture, and this is consistent with the Heisenberg's uncertainty principle. The second is that the wave function does not vanish. As you see in pictures like this, whether it is a square of the wave function or it is the wave function, you see that the wave functions vanish at certain points which are the roots of the Hermite polynomial, but they don't vanish otherwise, and the wave functions are finite even when x is very large. What it means is that even when the classical potential boundary has been exceeded, the probability of finding the oscillator in classically forbidden regions exists in quantum mechanics, and this leads to an interesting phenomenon called tunneling, but we will not worry much about it. The boundary for the oscillator is endless. That is important to remember. And since the wave functions do not vanish, the squares of the wave functions are also non-negligible, and that essentially means a likelihood of locating the oscillator outside the classical potential boundary regions. Okay. All of these are related to molecules when we study molecular vibrations, and we will see that the molecular vibrational energies are quantized, and this will be used to understand vibrational spectroscopy at an elementary level. Okay. At the end of this lecture and at the end of next lecture, there will be a few sample problems given so that you can understand the particle in a one-dimensional, two-dimensional box and harmonic oscillator through examples and probably through the solutions given here. Okay. Now we will move on to the most important topic that a chemist always has to worry about when studying quantum mechanics, namely the hydrogen atom. Okay. Obviously, it is the most important problem for chemists who want to understand quantum mechanics, because the hydrogen atom solutions are the fundamental solutions based on which all the other atomic energy level solutions and molecular energy levels are constructed. All the atomic orbitals which are concepts of the hydrogen atom Schrodinger equation are used throughout in chemistry, in everywhere, organic chemistry, inorganic chemistry, everywhere, in understanding why reactions take place the way they do, why bonding takes place the way it does. So the modern concept of chemical bonding basically originates from the solution of the hydrogen atom. Also, from the point of view of history, in quantum mechanics, the hydrogen atom is probably the only realistic system that could be solved analytically using the Schrodinger equations. The one-dimensional and two-dimensional particles are models. The hydrogen atom with the electron and proton stuck together due to Coulombic interactions is the only real problem, three-dimensional problem, that you can get exact solutions, exact analytic solutions. Therefore, this was extremely important, and its solutions were studied at great details. Even in this series of lectures, we will give considerable amount of time, 3 or 4 lectures extending over various aspects of the hydrogen atom, to see that how important it is in understanding the chemistry from the point of view of quantum mechanics. Okay. We will do mechanically what we have to do for at least the first part of the lecture. Mechanically meaning, let us set up the Schrodinger equation, let us try and see how to solve it. I am not going to give you again the solutions of the hydrogen atom in detail, the method of solutions of the hydrogen atom in detail, because that will involve understanding differential equations in a different level. We will not do that. We will again study only the final solutions and not the method of solving them. Okay. The hydrogen atom, the simplest classical picture you recall from Niels Bohr is that the electron keeps moving around the proton, positive charge, and the electron, negative charge. The particle nature of the hydrogen atom was emphasized in Niels Bohr's treatment, very rather ad hoc treatment, but it was the first one which looked at the solution from the standpoint of quantizing some of its energies. Classically, if you represent the hydrogen atom with the electron and proton with the separation or, the interaction energy between the proton and the electron depends only on the distance. Therefore, if you imagine a spherical atom of hydrogen with the electron moving on top of the sphere, the interaction energy between the nucleus at the center and the electron anywhere on the sphere of radius r is the same. The kinetic energy of the electron as it moves around in certain orbits, in classical, again from the classical perspective, the kinetic energy is again given by the p square by 2m, where p is the momentum, linear momentum associated with it. Even though the hydrogen atom moves in a bounded region, you can still associate a linear momentum with it, and you can express the classical kinetic energy of the hydrogen atom as simply px square py square pz square by 2 me, mass of the electron. Because the nucleus is very heavy, almost 2000 times heavier than that of the electron, let us deal with this problem with the assumption that the nucleus is stationary. If the nucleus is not stationary, it is moving, then you have to include its kinetic energy also in the process. We will not have to worry about this. We will treat the hydrogen atom as a stationary atom in the sense the nucleus is heavy, it does not move. Therefore, when you talk about the kinetic energy of the system, you are only writing the kinetic energy of the electron, okay, one electron. And the potential energy that the electron has in its interactions with the positively charged nucleus is of course the Coulombic interaction minus E square by R, because this is a nuclear charge with E, one positive, and Ze, I would rather write Ze as the nuclear charge. Z is the atomic number, the number of protons here, and E minus, and the electron nucleus interaction energy is attractive with the minus sign. This 4 pi epsilon naught is for taking into account the SI units. Epsilon naught is the permittivity, but we will concentrate on these, what is under the square root. That is the distance r. If you imagine the electron to move anywhere on a sphere, and if you associate the origin of this coordinate system with the nucleus, the origin is right here, 0, 0, 0. With respect to that, the electron coordinates are x, y, and z. Then the potential energy of the hydrogen atom, the electron nucleus interaction, is minus E square by 4 pi epsilon naught r. Because the kinetic energy is p square by 2m and it is now in 3 dimensions, we can write the quantum mechanical equation by changing the p into minus I h bar d by dx. Partial derivative now, and you are familiar with that from the particle in a 2-dimensional box. This has been mentioned already. Therefore, p square is now replaced by the 3 partial derivatives. P square by 2m is now written as minus h bar square by 2m. The partial derivatives dou square by dou x, the E referring to the electronic coordinate, plus dou square by dou y E whole square plus dou square by dou z E square. Okay. This is the kinetic energy. Then the potential energy is already written as minus E square by 4 pi epsilon naught square root of x E square plus y E square plus z E square, which is in spherical system, coordinate system, it is minus E square by 4 pi epsilon naught r. Okay. Therefore, one can write the Hamiltonian of the hydrogen atom, the electron in the hydrogen atom, one can write with the stationary nucleus immediately as the kinetic energy plus the potential energy, the kinetic energy plus the potential energy, which is minus E square by 4 pi epsilon naught r. Then the Schrodinger equation is obviously the equation that we want to solve is H psi, which is now a function of the electron position x E y E z E is equal to E, the constant energy, times psi of x E, y E and z E. The solution now of this differential equation is the differential equation containing p square by 2m acting on psi plus the potential energy minus E square by this acting on psi, giving you the E psi. Okay. The differential equation is rather complex. We will not be able to go through the process of solving it. The thing that one finds in dealing with such types of equations where the derivatives are all additive, no cross derivative dou square by dou x E square, but there is no derivative like dou by dou x, dou by dou y. When the derivatives are all additives and the rest of the term contain separable quantities, if we use spherical polar coordinate system, you would see that this contains only r, the radial distance in spherical polar coordinate system. Therefore, the solution of this problem is probably more easily accomplished in spherical polar coordinate system than it is in Cartesian coordinate system, because in Cartesian coordinate system you have a square root involving all the 3 coordinates. Okay. The spherical coordinate system is the polar coordinate system, that spherical polar coordinate system, and let me give you a little bit of what r, theta and phi and how I'm sure you have studied that earlier, coordinates, different types of coordinate systems, but let us look at what the r, theta, phi, how they are defined and how the equation can be transformed into the r, theta, phi representation. Okay. It's because, remember, it is this kind of separation is possible because the Coulombic potential energy is dependent only on the distance from the nucleus, radius. Okay. This is not a sphere, but anyway, you will see in a minute in an animation you will see the actual sphere. The construction of the spherical polar coordinate system, let me explain with that animation. Okay. If the z axis or the polar axis is represented like this, and the x and y axis, this is a right-handed coordinate system. Any point r, any point represented by the radius vector r, can be decomposed along the x-axis, y-axis, and the x-axis, y-axis, and the z-axis through the theta and phi. Theta represents the polar angle, which is from the polar axis. Theta is 0 to pi, to the negative axis. From north pole to south pole, if you recall the association with earth. The phi represents the axis which rotates, which is basically a circle. When you section the sphere perpendicular to the polar axis, the phi represents the 360-degree rotation. That is the other coordinate. Let's see it clearly in one of these animations. Yeah, in this animation that you will see now, let me represent to the polar angles phi and theta. The angle phi is with respect to the x-axis, that is an axis perpendicular to the polar axis. The angle phi is defined as 0 to 360 degrees. Let's see that here. So phi equal to 30, 60, 90, and so on. So that's the phi axis. The phi axis represents an axis which is that is a plane which is perpendicular to the polar axis and represents all the 360-degree rotations about that. Now the theta axis, the value for theta is with respect to the polar axis. That's the theta representation. You see that theta is 0 to 180 degrees and phi can be any one of these from 0 to 360 degrees, and if you travel through both of these coordinates, you generate the entire surface area of the sphere. You generate the entire surface area of the sphere when you go through this. So the values of the coordinates are, for spherical system, the radius of the sphere r. Here we have assumed one particular radius and therefore we have drawn a sphere of that radius. For that any radius, the value for theta is, the variations are from 0 to pi, and phi the values are from 0 to 2 pi. And the radius of the sphere of course can be from 0 to infinity. So this generates the entire three-dimensional universe. Okay. These are the accessible regions for the electron in the hydrogen atom, in exactly the same way that you had accessibility for a particle in a one-dimensional box from x is equal to 0 to x is equal to L, or in the harmonic oscillator from x is equal to minus infinity to x is equal to plus infinity. Okay. Now the three-dimensional region in spherical polar coordinate system, these are the variables that you have to remember. Let us now look at the other animation on the coordinates. How we get this r sin theta sin phi, r sin theta, r cos theta, etc. Let's write that by looking at this movie carefully. Okay, what you have there is an arbitrary position or a radius vector r anywhere on the sphere, okay, making an angle theta with respect to the polar axis z. Therefore, its projection along the z axis is going to be r cos theta, and its projection perpendicular to the plane. This is an arbitrary position, so it can be anywhere, and this is going to be r sin theta. but now the phi value is an arbitrary value phi from the x axis. Therefore, r sin theta will have a projection along the x axis as r sin theta cos phi. Okay. That is the x axis projection, and the y axis projection is of course 90 minus phi is this angle. So, that is r sin theta cos 90 minus phi or r sin theta sin phi. Okay. So, this is what you have in the final frame, that the coordinates, the spherical coordinates are x is equal to r sin theta cos phi, y is r sin theta sin phi, and z is r cos theta. Okay. These are the coordinate transformations that one has to remember in switching from the usage of x, y, z coordinates to the coordinates r, theta and phi. Of course, you can easily invert them. The inverting this procedure, that is, if you want to express r in terms of x and y and z, you know that if you take x square plus y square plus z square, you are going to get r square sin square theta cos square phi plus r square sin square theta sin square phi plus r square cos square theta, which gives you r square. Therefore, r is square root of x square plus y square plus z square. Not a surprise, you have already used this result in writing down the potential energy 1 by r, 1 by square root of x square plus y square plus z square as 1 by r. It is obvious. What about theta? If you take the ratio of y by x, you get tan phi. Y by x is tan phi, or phi is or tan inverse y by x. So, now you can express r in terms of x, y, z, phi in terms of x, y, z, and the last one is of course theta. Square root of x square plus y square will give you r square sin square theta cos square phi plus sin square phi square root. So, what you get is r sin theta, and you know z is r cos theta. Therefore, the ratio of these two gives you tan theta, which is square root of x square plus y square by z. Therefore, theta is or tan square root of x square plus y square by z, which is also, instead of or tan you also write tan inverse. Okay. So, these coordinate transformations are important, because when we write the Schrodinger equation in Cartesian coordinates, and when we want to change the Schrodinger equation into spherical polar coordinates, because the potential energy depends only on r, we must remember these transformations. We must be able to switch between these two. That is all I will explain. I will not tell you how to derive the kinetic energy operator in spherical polar coordinates. And from my experience with our own students in IIT, I can tell you, you will have to spend roughly about 5 to 6 hours to go through the process of deriving the Schrodinger equation in spherical polar coordinate system from that of the Cartesian coordinate system, if you do not make any single mistake. If you make a mistake, the 6 hours will have to be reproduced again in some other time. So, let us not do that, but just get the result of what the equation looks like in spherical polar system here. Okay. So, what you have here is, of course, both the kinetic energy and the potential energy of the hydrogen atom electron represented now using spherical polar coordinate system. The derivation of this is not important for this lectures. You should be able to do it when you understand partial differential equations and when you understand how to transform between coordinate systems using Jacobians, etc. We don't need to, this is basically partial derivatives. You should be able to transform from one set of coordinates to another set of coordinates using the chain rule of partial differentiation. We will not worry about that as chemistry students. We will believe that the physicists and the mathematicians have done it right, and therefore we will take this equation as God given or as the physicist given. We will believe that this is right, let's work on this equation. Okay, the form of the equation is something that we should write down just to familiarize ourselves with the notation. Okay. The Hamiltonian H psi, now psi is expressed in terms of r, theta and phi. Okay. H psi is equal to E psi or theta and phi is to be written now. The Hamiltonian operator is the expression given minus h bar square by 2m, okay, times, this is going to be fairly long, 1 by r square dou by dou r square dou by dou r, okay, plus, we will write it below, 1 by r square sine theta dou by, let me see, it has to be dou by dou theta sine theta dou by dou theta plus the expression is 1 by r square sine square theta dou square by dou phi square plus e square by 4 pi epsilon naught or 2m by h bar square. It only gives you time to write these equations and try and understand. This is the operator h containing a derivative expression in r, a derivative expression in theta, and a derivative expression in phi, and a potential energy term involving r. The process, the painful process of going through this transformation is to ensure that the wave functions that we are trying to obtain can be separated into functions depending only on r, functions depending only on theta, and functions depending only on phi. So what one tries to do is to simplify the wave functions by separating them into independent coordinate dependent functions only, and this is a process you are familiar with from particle in a two-dimensional box where you represented the wave function for this solution of this equation minus h bar square by 2m dou square by dou x square plus dou square by dou y square psi of x comma y. This equation, please recall from the earlier lecture that you represented psi of x y as a function which depends only on x and a function which depends only on y, and the product of these, and this enabled you to write two one-dimensional Schrodinger equations and then study the solutions rather straightforward. Okay. So in the same way we try to use the right coordinate system in which the wave functions can be expressed rather simply and then study the solutions in that coordinate system. All the atomic orbital pictorial representations that I will give are given in spherical polar coordinate systems, and the underlying mathematics is given here. Now there is a notation here. This is the H operator. So when you write H psi is equal to E psi, what it means is that this operator acting on psi, so if we write this as H psi, this whole thing is operating on psi to give E psi. What does this mean 1 by r square dou by dou r square dou by dou r psi? What does that mean? It means the following: 1 by r square dou by dou r square dou by dou r psi. That is the first term. Okay. And this of course is a compact notation, and you can expand this. In solving the equation you have to anyway do this. The differential now will act on uv kind of a product, so you can have it as a dou square by dou r square psi, or sorry, in addition you have this one more term 1 by r square, and there is an r square here because this differential acts on this. Now if the differential acts on r square, what you have is 2r dou psi by dou r, which is dou square psi by dou r square plus 2 by r dou psi by dou r. This is the expression which is represented by a compact form like that. Okay. So that is what is given here when you write minus h bar square by 2m 1 by r square dou by dou r square dou psi by dou r. What it means is the derivative expression minus h bar square by 2m 2 by r dou psi by dou r plus dou square psi by dou r square. Likewise, when you write 1 by r square sin theta dou by dou theta sin theta dou psi by dou theta, what it means is the derivative expression which has to be expanded exactly like what you have done here, and it gives you minus h bar square by 2m cos theta r square sin theta dou psi by dou theta plus 1 by r square dou square psi by dou theta square. Okay. We will not solve the equation today. We will not solve the equation in this course. We will rather give the solutions of this equation in the next couple of lectures with corresponding pictorial illustrations, and I will also tell you a little bit about the method of solving the differential equation, how we separate the wave functions into products of 3 different functions, and how we obtain the final result, what is the final result, and then we will try to picture the final result in this whole process. Okay. So the sum and substance of today's lecture is that we talked a little bit about the harmonic oscillator, extended what was done in the previous lecture by way of pictorially representing the wave functions, the harmonic oscillator wave functions and the squares of the wave functions. And we noticed that the squares of the wave functions have certain properties which are not what you would expect when you associate them with the corresponding classical solutions using Newton's laws. Okay. So the harmonic oscillator quantum mechanics presents some things which are difficult to digest for a physicist or a chemist who is well versed with a classical harmonic oscillator. This was then followed by focusing on the problem of the hydrogen atom. What is it that is going to be important for us as chemists is that the stationary nucleus with the electron moving around in the classical sense being now replaced by a quantum mechanical wave function, and the Hamiltonian, the Schrodinger equation that one needs to solve being the h psi is equal to E psi. We will continue this in the next lecture. At the end of this lecture you will see some problems which are related to the last 4 lectures, and the solutions will be given some time later. There will be enough time for you to solve them. Until then, thank you very much.